2PARMA project is a 3-year European project started in 2010 under the leadership of Politecnico di Milano, with the goal to develop programming paradigms, tools and runtime support for many core systems. All concepts and tools developed in the project have been evaluated on a multimedia use case and a cognitive radio use case, and a set of industrial hardware platforms, including Platform 2012, provided by ST Microelectronics. These technical objectives have been fully met, even exceeding expectations. At the end of the project, 2PARMA has been considered a success story, worth showing as an example of best practice in the FP7 European projects.
During the 2PARMA project, we have to overcome many obstacles to achieve the challenge of enabling the use of multi-core architecture to realize embedded system capable to be adaptive at runtime, energy effective and easy to be programmed. In particular, one of our aims has been to make available to the community the output of the project and, at the same time, to achieve a good synergy with the industrial partners to achieve a real exploitation of the results. Hence, we developed a runtime manager capable to run on multi-core system, in particular the one provided by ST Microelectronics, but also on any x86 architecture. And this is made available as open source, as an open source framework. Moreover, a compiling toolchain based on OpenCL has been made available to program a parallel architecture on multi-core architectures. From the industrial side, this software will be made available to the customer, and more in general, the methodology developed during the project will be applied to the 3 representative architecture of the project: the STORM architecture provided by ST, COBRA provided by IMEC, and, as I said, to any x86 architecture. And also we are exploiting the MOST toolchain for automatic design space exploration. In summary, the expected impact of the 2PARMA project can be quantified in terms of 50% reduction on the parallel application development time, including the integration with the runtime resource manager, up to 60% reduction of the compiler toolchain development time, thanks to the adoption of LLVM technology, an effective control of the stability and robustness of the runtime resource manager with an overhead that is always below 10%, and in many of the cases, we observed an energy reduction of the application execution on multi-core platforms up to 40%.
The goal of the 2PARMA prototype is to provide evidence about the broader applicability of the tools and techniques developed within the project. We wanted to demonstrate the integration of the runtime resource manager, runtime monitoring, dynamic memory management, and the OpenCL toolchain. One of the possible applications of the final 2PARMA prototype is video surveillance and video analytics. We assume to have a moving object that is captured by 2 cameras, left and right, and the stream is elaborated by a multiple application that computes the distance of the object with respect to the surveillance theme. As the object approaches, the resolution is increased in order to enable a better compression. The runtime structure of the prototype is composed of Barbecue, the runtime resource manager, 2 SVC decoders for decoding video, the multiple application for decoding the distance of the objects, and an application-specific runtime manager. Besides, we have a dynamic memory manager, and we support 2 runtimes, OpenCL and Mind. The resource managers used within the prototype are able to provide an optimal resource usage as the object approaches the cameras. We integrated a dashboard within the prototype to be able to look at the resource usage of the applications and the resolution and frame rate provided by the system itself. As we're going to see in the following part of this video, the prototype works best when both the runtime resource manager and the design space exploration are used.
First, we start the Barbecue Runtime Resource Manager, which initializes the multi-core platform into a host node for system processes and 1 or more device nodes where the applications will be deployed. This is the output of the prototype. In the left window, the decoded video captured by one of the stereo cameras shows the surveyed area. In the right window, we show the runtime configuration of the SVC decoders and multiview. At the beginning, nothing is happening in the scene, So the configuration ID of the SVC decoders is 0, which corresponds to the lowest SVC layer. This is why the quality of the output frame is poor. In the multi-view configuration, you can see that the power saving mode is on, which means that multi-view is disabled. Then we start the prototype, which will remain in the power saving configuration until any possible threat is detected in the scene. This is the case when a person enters the surveilled area, which triggers a reconfiguration of the system. Now the system is running in a mid-distance configuration since the detected object is moving away from the cameras. In this configuration, multi-view ensures a response time less than 1 second, while providing a good quality of service, which means an accurate estimate of the distance. The long-distance configuration, when the object is far away from the cameras, brings the system back to the power-saving mode. Another person enters the area, so the system is reactivated. The previous person is approaching the cameras. When he gets over a distance threshold, then the highest configuration will be triggered. Now, you can see that the SVC decoders are decoding the highest layer, which corresponds to 15 frames per second, while before the frame rate was 7.5, and at the same time the quality of the output video is much better now. The time constraint on multi-view is higher, so the application-specific monitor reduces the accuracy of the distance estimate to meet the frame rate goal, 2.5 frames per second. The goal is met since the measured frame rate is above the goal, which provides a response time less than 500 milliseconds. In this plot, we compare our prototype above with the baseline version that does not use the barbecue runtime resource manager below. The multi-view runtime requirement, frame rate, depends on what is detected in the scene, so it should be the same since the input video used for the two implementations is the same. A first result is that our proposed prototype is more stable at runtime in following the frame rate goal. Beside that, the baseline version misses a possible threat in the scene, which is when the second person gets close to the cameras. Indeed, the frame rate goal is not increased to 2.5 frames per second as in our proposed prototype. This does not guarantee a good response time in the baseline version.
2PARMA project will provide the European citizens with faster and lower power consumption devices for multi-application scenarios and will help a major European player such as ST Microelectronics in establishing an innovative many-core computing platform with a large user community equipped with the bleeding-edge software tools for application development.